Think about the last time your computer crashed right in the middle of an unsaved project.
Oh, the worst.
Right. Or the last time you tried to dictate a simple text message and the AI just completely misunderstood your intent, sending something entirely nonsensical.
And you get that exact physiological feeling.
Yes, exactly. Your jaw clenches, your heart rate spikes, your breathing gets, a little shallower. For decades, we've just kind of accepted this as the cost of doing business with machines.
Yeah, I mean, we treat ourselves as the chaotic variable that needs to be disciplined, right?
Mm-hmm.
Rather than demanding the machine adapt to us.
Precisely. We have spent our entire lives adapting our human bodies, our nervous systems, and frankly, our patience to the rigid, unforgiving logic of binary software. And what happens?
We sit there staring at a blinking cursor in a void.
Waiting for a prompt, fighting through information overload. But what if a machine could actually read your biological and semantic tension? What if it could adapt its own level of autonomy to calm you down rather than, escalating your stress?
Which brings us to the topic of today's deep dive.
Exactly. For you listening right now, that is the exact premise of the systems engineering breakthrough we are going to dissect today. Let me set the scene for you.
Go for it.
It is pouring rain here in Alexandria, Virginia. We've grabbed a quiet, dimly lit corner booth at a tavern just a stone's throw from the United States Patent and Trademark Office campus.
It's a very familiar haunt.
It really is. Frankly, after a long week of reviewing incredibly dense software patents as a primary examiner in Art Unit 2100, which handles computer architecture and graphical user interfaces, I needed a quiet place, a stiff drink, and most importantly, I needed to bring a specific stack of documents to this table.
And as a retired HCI, that's Human-Computer Interaction and Cryptography patent attorney, there is honestly nothing I enjoy more than taking a primary examiner's quote-unquote revolutionary patent stack and ruthlessly tearing it apart over a pint.
Which is exactly why you're here. Spread out on the wooden table right in front of us, we have the provisional and utility patent specifications for a system codenamed CIP-003.
Heavy reading for a Friday night.
Oh, absolutely. Alongside the formal claims, I brought the internal architectural memos, famously known amongst systems engineers as the Cathedral of Code, and the academic preprint paper detailing the underlying mathematics, which is titled The Marshall Triangle.
So the mission for our deep dive tonight is pretty complex then.
Very. This system, which is part of an AI interface known as Quetra, claims to solve the problem of human-AI shared autonomy.
Okay, I'm going to stop you right there.
I thought you might.
Yeah, because sovereign AI is one of those terms that just immediately makes my eye twitch.
Fair enough.
In my decades of litigating and prosecuting software patents, sovereign AI is almost universally marketing terminology for, we decided to run a local language model on your phone. It's a buzzword. It's not a patentable mechanism.
I completely agree with your skepticism. I sit in Art Unit 2100, and I can tell you with absolute certainty that 90% of the graphical user interface patents that cross my desk are just basic mathematics rendered on a screen.
Abstract ideas masquerading as a machine.
Exactly. And they get summarily rejected under Section 101 of the Patent Act, specifically under the Alice Framework. When I first read the preamble for CIP-003, I honestly laughed.
Really?
Oh, yeah. I looked at this concept of a triadic balance math measuring user preferences, and I thought, well, this is just a digital mood ring.
Right, an abstract psychological profile mapped to a graphical interface.
Exactly. I was ready to stamp a rejection on it before my morning coffee.
But you didn't.
I didn't, because the deeper I got into the dependent claims, the more I realized I was looking at a legitimate systems-level paradigm shift.
Well, I am going to hold your feet to the fire on this one.
I expect nothing less.
I came into reading this stack of sources completely ready to tear it apart under Section 102 and Section 103 for prior art obviousness. But I will concede one point right out of the gate.
Which is?
The way this system's mathematics directly gate the compute routing, and particularly how they manage the low-bandwidth accessibility layers, is mathematically ironclad.
It physically alters the execution of the machine.
It does. But to prove to our listener that this isn't just an abstract idea, we cannot start with the flashy interface. We have to start in the absolute basement of the architecture.
The data contract. Because if the foundational data structure that drives this entire system is deemed abstract by the USPTO, the whole patent fails at step 1 of the Alice test.
The interface wouldn't matter. The routing wouldn't matter.
Exactly.
So let me put on my devil's advocate hat and probe the core premise of this architecture. The patent describes mapping user interactions across 3 distinct axes, right?
Privacy, performance, and personalization.
Yeah. On its face, to any patent examiner or federal judge, that sounds like a purely mental process.
It does sound a bit like a personality test.
It sounds like giving a user a quiz, tracking their preferences, and displaying a result.
Ah,
The courts have ruled time and time again that organizing human activity or tracking psychological preferences is an abstract concept.
right.
So how on earth does tracking a user's preference for privacy survive a Section 101 challenge?
That is the million-dollar question, and it is the exact rejection I was actively drafting in my head. Under step 1 of the Alice framework, you ask, is the claim directed to an abstract idea?
And yes, arguably, tracking a privacy preference is abstract.
But the magic happens in step 2. Step 2 asks if there is an inventive concept that transforms that abstract idea into a concrete application that fundamentally improves the functioning of the computer itself.
Right, the EnFish standard. You have to prove the software makes the computer run better, faster, or more securely in a way that prior art did not.
Exactly. And this is where CIP-003 structurally diverges from a personality quiz. This triadic mass does not just sit in a database looking pretty.
What does it do then?
It is explicitly tied to non-obvious improvements in computer functionality. It algorithmically drives independent visual pacing engines. It dynamically alters the physical hardware routing of the computation. And it governs accessibility gating at the silicon level.
So the preference is actually a cryptographic and routing governor.
Spot on.
All right, I'll accept that premise for a moment. But to verify it, we have to deconstruct the actual data contract they use to capture this information.
In the Cathedral of Code memos, they refer to it as the node state contract.
Right, the no-state contract. And what is genuinely fascinating here is the triadic spine of this contract. When a user interacts with the system, it doesn't just record a binary click or a text string.
No, it records 3 simultaneous continuous dimensions of that human interaction.
Will, semantic content, and emotional valence.
If we're going to convince you listening that this is a hardware-level innovation, we really need to break those 3 down meticulously. Let's start with will. What does that mean in a systems engineering context?
Well, will is the directional intent and the execution force behind an action. Think about traditional interfaces.
Like just clicking a mouse?
Yeah, if you click a mouse, the computer registers a 1, the button was clicked. The system doesn't know if you confidently clicked it, if your hand was shaking violently when you clicked it, or if you just accidentally brushed the trackpad.
Right, it's just binary.
Exactly.
Yeah.
But the node state contract measures the strength, the modality, and the physical confidence of that input.
And then we move to semantic content, which is the actual meaning of the interaction.
Right, but it goes far beyond just parsing the text of a query. It encapsulates the text, the historical context references, and crucially, the system's own self-assessed confidence in its interpretation of that meaning.
So if you ask an AI to, say, shoot off that email to the board,
The semantic content axis doesn't just log the command. It logs a metric of how certain the AI is that it knows which email and which board you mean.
which leaves the third axis, emotional valence.
This is the affective or somatic state of the user at the exact microsecond of interaction, and it's heavily coupled with the temporal phase of the interface's pacing engine.
Now, I can hear the skeptics in our audience right now.
Oh, I'm sure.
Measuring intent, meaning, and emotion sounds incredibly heavy computationally. If you are loving that amount of metadata for every single micro-interaction, you are going to choke the processor of any standard edge device. But what makes this patentable is not just what they are collecting, but how it is structurally formatted. The node state is entirely serialized into an Apache Arrow-compatible columnar format.
I will admit, when I read the word Apache Arrow in the utility specification, I sat up a little straighter.
It's a big deal, right?
That's a massive technical distinction that pulls this out of the realm of abstract ideas and into hardcore database engineering.
It changes everything. For you listening, let me offer an analogy to ground this. Think of traditional row-based data storage like a written diary.
Okay, diary.
If you want to find out how many times you felt confident on a Tuesday in November, you have to open the diary, read page by page, paragraph by paragraph, parsing all the irrelevant text about what you ate for lunch just to find those specific data points.
The processor has to load the entire row into memory just to read one attribute,
Exactly. It's slow, it causes massive latency, and it drains battery life.
which is the death knell for real-time continuous interface pacing.
Exactly. Now, think of an Apache Arrow columnar format like a highly organized, standardized filing cabinet where every folder is perfectly identical and sorted purely by category.
So all the Tuesday data is in one drawer.
All the confidence data is in another. Because the data is stored in columns rather than rows, the processor can just grab the exact drawer it needs without reading the rest of the diary.
But more importantly, Apache Arrow is language agnostic.
Yes.
It uses identical memory formatting across entirely different hardware environments. It allows local devices and secure cloud environments to read and analyze massive amounts of data instantly without having to unpack, translate, and repack the data.
In systems engineering, we call this zero-copy exchange.
And that zero-copy exchange is the beating heart of the system's speed. This no-state contract has to be instantly queryable by the system to make split-second hardware routing decisions without introducing even a millisecond of latency.
Because if the system has to pause and translate your data to figure out if it is allowed to route a query to the cloud, the illusion of shared autonomy is broken.
The columnar serialization is what makes the continuous tracking viable on a dedicated hardware companion.
So we have a highly efficient database structure, but I want to steer us back to the will axis for a moment.
Okay, sure.
Because you mentioned earlier that the way the system handles low bandwidth accessibility is what hooked you. And this is where the patent dances right on the edge of a very strict boundary. BCI, or brain-computer interfaces.
Yeah, they are incredibly careful with their phrasing here. The patent specification explicitly refers to telepathy-class BCI input compatibility.
Right.
It is crucial to understand that they're not implying a direct neural implant is the default, or that they are patenting the neural hardware itself. They categorize BCI strictly as an optional alternative input modality that maps directly to the low bandwidth accessibility layer.
Which makes total sense. BCI is essentially the lowest bandwidth, highest noise input device you can possibly use.
Exactly. Neural signals are notoriously noisy. If I have an optional BCI headset on and I think the command click, the actual neural waveform the computer receives might be incredibly fuzzy.
And in a traditional interface, a fuzzy click is a failed click. The system throws an error, the user gets frustrated.
The biometric feedback stress loop begins.
Precisely. But what is brilliant about the node-state contract is how it mathematically separates signal confidence from semantic confidence.
I want to make sure the listener fully grasps the magnitude of this separation, because it is a phenomenal accessibility breakthrough.
Let's unpack it. In a traditional GUI, the physical action and the intended meaning are fused. If my hand slips while clicking a mouse, the computer assumes I intended to click whatever I accidentally hit.
The physical error corrupts the semantic intent.
Exactly. But CIP-003 essentially asks the system two distinct parallel questions. First, was the physical or neural click noisy?
That's the signal confidence check.
Right. And second, did the AI actually understand what the user meant within the broader context of the task?
And that is the semantic confidence check.
So let's look at a real-world application. Imagine a user with severe motor impairments, perhaps someone with Parkinson's disease experiencing heavy tremors, or someone relying on a dwell select or stand cycle accessibility tool using eye tracking or a noisy neural cursor.
Their signal confidence is going to be consistently low. The physical execution is messy.
In a traditional system, that user is constantly punished by the interface. The system rejects their inputs, forcing them to try again and again, causing massive cognitive and physical fatigue.
But because the node-state contract isolates signal confidence, the system says, okay, the physical input was messy, the signal confidence is at 20%. However, based on the conversational context, the cursor proximity, and the historical data, my semantic confidence in what they are trying to achieve is at 99%.
It doesn't throw out the input just because the physical execution was flawed. It honors the intent over the mechanical failure.
The data contract doesn't break, and the user is not punished for the limitations of their input modality.
From a patent perspective, this is a massive win. You're taking a well-known problem in accessibility noisy input and solving it not by changing the hardware, but by fundamentally restructuring the data contract to isolate variables that previous systems conflated.
That is a concrete technical solution to a technical problem. It easily survives step 2 of the Alice test.
I'm glad you agree, because this is where the conversation usually gets very heated in Art Unit 2100. We've established that the node-state contract is a rigorous, Apache Arrow-compatible columnar data structure that solves concrete computational and accessibility problems.
The data foundation is solid.
But raw data is useless to a human being. Once that data is securely serialized, the system has to visualize these competing triadic values, privacy, performance, and personalization back to the user without overwhelming them.
Which brings us to the geometric engine of the interface, the Marshall triangle.
Yes.
And this, my friend, is where I initially brought out my red pen. I was absolutely ready to draft a Section 102 and Section 103 obviousness rejection.
I have been waiting for this. Lay out the attack. If you were the examiner, why would you reject the Marshall Triangle?
Because triadic visualizations are not novel, not by a long shot. The history of science is littered with them. If you look at James Clerk Maxwell's 1860 color triangle, he mapped the primary colors of light to a triangle over a century and a half ago.
It's true.
If you look at any standard barycentric ternary plot used in physical chemistry, geology, or metallurgy for the last 100 years, you see three competing variables mapped to a triangular coordinate system. It's standard practice.
So you're saying it's obvious.
My immediate question when reading the claims was, how is mapping privacy, performance, and personalization to a triangle any different from mapping sand, silt, and clay on a soil texture triangle? Why doesn't standard barycentric prior art completely invalidate this claim under obviousness?
That is a highly aggressive textbook 103 rejection, and it's exactly what a Federal Circuit judge would ask. But this is where I passionately defend the novelty of the CIP 003 specification, because it all comes down to a structural innovation called the midpoint source inversion.
A midpoint inversion just sounds like rotating the coordinate plane. You can't patent rotating a triangle.
It is not a visual rotation.
Yeah.
It is a fundamental inversion of the underlying logic and the resulting mathematical field. Let's visualize those classical simplex models you just mentioned. In Maxwell's triangle, or a standard metallurgical plot, where do the primary influences sit? Where are the pure states?
They sit at the three vertices, the absolute corners of the triangle. The interior space is just a calculation of the blend between those three dominant corners.
Exactly. The corners are the source of power, but the Marshall Triangle entirely inverts this logic.
Inverts it how?
The primary system values, the pure state of privacy, the pure state of performance, and the pure state of personalization, are not anchored at the corners. They're mathematically anchored at the exact midpoints of the triangle's edges.
I see what you're saying, but you're going to have to prove to me how anchoring them at the midpoints actually changes the computational output.
Right.
Because right now, it still just sounds like a UI gimmick.
It changes the output drastically. Because the sources are at the midpoints, the vertices, the corners of the triangle, cease to be pure states. They emerge only as secondary, pairwise hybrid blends.
Wait, let me visualize this. If privacy is anchored at the bottom edge midpoint, and personalization is anchored at the right edge midpoint,
then the corner sitting between them is no longer a primary value. It becomes a highly saturated hybrid state representing the maximum tension between privacy and personalization.
Oh, I see.
In standard barycentric math, moving toward a corner means you are getting closer to a pure variable. In the Marshall Triangle, moving toward a corner means you're moving into a state of extreme conflict between two variables.
It creates a continuous high-tension field of influence rather than partition zones of dominance. It completely changes how the diagnostic displacement vector is calculated.
Exactly.
Okay, I am starting to see the mathematical divergence. But a continuous field needs an origin point, right? It needs a way to measure the tension. In a standard geometric plot, you measure distance from the absolute mathematical center of the triangle.
Right, but the Marshall Triangle does not use a universal center. It uses a dynamically calibrated white point.
Let's expand on this for the listener, because the term white point is doing a lot of heavy lifting here.
Yeah, break it down.
If we connect this to the bigger picture of shared autonomy, the mathematical center of this interface is not zero. It is not an objective universal origin that applies to every user equally. The white point is a dynamically calibrated, user-specific point of neutral recombination.
So how does that calibration actually work in practice?
When a user first configures the system, or as the system continuously learns their baseline through the node state contract, it evaluates their unique tolerance for these three axes. Some users might inherently prefer a system that leans heavily toward privacy, even if it costs them some performance.
Makes sense.
The system takes that baseline preference and sets it as the white point. That specific location on the triangle becomes neutral for that specific user.
It is their personal equilibrium.
Exactly. And from an engineering perspective, the system is continuously calculating an out-hunter displacement vector relative to this specific white point.
Measuring the distance.
It is measuring the exact mathematical distance and directional vector between where the user's baseline wants the system to be and where the system currently is operating. That displacement vector is what we call tension.
And I actually got to test the visualization of this tension. For you listening, I highly recommend digging into the live environment the inventors built to prove this out.
Where is it hosted?
It is hosted at marshalltriangle.app, and there is a broader systems architecture view at app.quetra.ai. I spent hours over the weekend playing with the live parameters to see if the math held up under extreme conditions.
What was the live rendering experience like? Did the client-side rendering choke when the tension vectors spiked?
Not at all. It is entirely client-rendered using an SVG Gaussian color field, which is incredibly lightweight. But while I was testing it, I noticed a brilliant technical save buried in the rendering logic that completely evades another massive piece of prior art regarding radial basis functions.
Let me guess. They solved the color washing problem.
Exactly. They solved it beautifully. Let me give an analogy for the listener. Imagine you are a lighting director in a theater.
Okay, I like a theater analogy.
You take 3 differently colored spotlights, a red one, a green one, and a blue one, and you shine them onto the center of a dark stage. Where they overlap, they blend smoothly into a white light in the center.
Yeah.
But if you take that red spotlight and you push the intensity way too hard, say you crank it to maximum power while the others stay dim, it floods the entire stage. The whole floor just turns a blown out, washed out pink. All the crisp edge definition between the colors is completely lost.
In mathematical terms, when you use a standard radial basis function to map a color gradient, heavily skewing one variable overwhelms the surrounding vectors. The gradient map washes out.
And the diagnostic utility of the visualization is destroyed because the user can no longer discern the subtleties of the state.
Right. If your system is heavily prioritizing privacy, the whole interface just turns a solid glowing hue. You lose all diagnostic nuance.
So the inventors of CIP-003 implemented what they call an adaptive sigma algorithm.
How does the sigma scale?
When the Marshall triangle detects that it is heavily skewed, let's say the system is pushed into a pure privacy emphasis state, minimizing performance to protect data, the algorithm dynamically scales the width of the Gaussian falloff.
What are the numbers?
Under neutral conditions, the sigma sits at 0.30. But as the tension vector increases and pushes toward an edge, the system scales the sigma up to a maximum of 0.48.
So they are dynamically widening the beam of the dominant source as it intensifies.
Precisely. By widening the falloff mathematically shifting from 0.30 to 0.48, it prevents the color field from blowing out the entire triangle. It forces the dominant color to maintain an incredibly sharp, defined edge against the weaker variables.
Maintaining a beautiful, legible gradient even in maximum tension states.
Yep.
It's mathematically elegant. I have to concede that point. The midpoint source inversion, combined with the adaptive sigma scaling, creates a novel graphical output based on non-obvious mathematical operations.
So it's not just a UI trick.
No, it is a computational necessity to keep a complex diagnostic tool legible on a dynamic edge device.
So let's take stock of where we are. We have a highly efficient columnar data contract in the node state. We have a novel inverted geometric visualization that avoids classical ternary plot prior art, and we have a dynamically scaling rendering engine. We have proven this is a robust system.
But this raises a fundamental psychological and ergonomic question. And honestly, it is the question that sinks most biofeedback patents.
The cognitive load.
Exactly. Staring at a high-tension diagnostic map while you're actively trying to work, write, or communicate is incredibly taxing.
Yeah, it would be exhausting.
If that Marshall triangle is glowing a bright, saturated hue because my system performance is lagging or my privacy is at risk, that is visually distracting. How does the patent handle the user's ambient attention?
Because if the interface stresses the user out, the entire premise of physiological attunement is a complete failure. And that transition brings us directly to Claim 11 of the utility specification. I will go on record saying this might be my favorite part of the entire patent because it addresses the most catastrophic flaw in almost all prior art regarding biofeedback and wearable user interfaces.
And that flaw is the biometric feedback stress loop.
Yes. For you listening, we need to spend some time on this because this loop is the reason why so many smart wellness devices end up in a drawer after a month. Let's unpack the psychology of it.
In conventional biofeedback systems, think of early heart rate wearables, stress-tracking smartwatches, or mood-tracking mobile apps. The interface logic is binary.
That's so.
If the system detects user distress, or if the system itself is under high computational tension, a primary UI element flashes a warning color. Usually it is a bright red or an amber alert. The intention of the software engineer is simple. Alert the user to the problem.
It's the check engine light philosophy.
Exactly. But human physiology does not work like a car engine. When a human being sees a flashing red warning light that is explicitly associated with their own physical or psychological state, their nervous system reacts.
They're cortisol spikes.
Their heart rate accelerates. The user's stress actively increases as a direct result of seeing the warning.
And then the system reads that new higher stress level.
Yes. The system sensors read the increased heart rate, process it as escalating distress, and flash an even brighter, faster red light.
Which causes more stress, which causes a brighter light.
And suddenly, the user and the machine have spiraled out of control into a biometric feedback stress loop. The interface actively harms the user it is trying to assist.
It is a massive design failure in the industry.
And it happens because engineers treat human biology like a purely logical data stream.
It is a profound failure of empathy in systems design. But Claim 11 of CIP-003 introduces a structural solution they call the separation principle. The genius here is not in what they display, but in how they aggressively decouple the information.
The patent structurally separates ambient pacing from chromatic diagnostics.
Yes, they are two entirely separate visual and computational pipelines that never intersect visually.
Let's visualize this for the listener. How is the ambient pacing visualized, if not with color?
Through what the inventors call the Ma experience breathing orb. If you are looking at the interface, this orb is the primary visual anchor. It is the element your eyes are drawn to 90% of the time.
And the critical patentable claim is that this primary orb is strictly constrained to achromatic luminosity.
Meaning it only ever changes in brightness. It pulses from dark gray to white. It never, under any circumstances, turns red, green, or blue.
Exactly. No matter what is happening in the system, no matter how severe the privacy breach or how stressed the user is, the orb remains achromatic.
Furthermore, it pulses on a highly specific asymmetric 1.2 ratio. Specifically, a 4-second inhale phase where it brightens, and an 8-second exhale phase where it dims.
The 1.2 ratio is not arbitrary. That specific respiratory pacing is clinically proven to engage the human parasympathetic nervous system. It acts as a vagal nerve brake, physically signaling the body to calm down.
Right. And because of the separation principle, that orb is an unconditionally calm, reliable anchor and never betrays the user by flashing red.
But then where does the tension information go? The user still fundamentally needs to know if the system is misaligned or if a privacy threshold has been breached. You can't just hide critical system alerts.
All of the tension-derived color information, the output of the Marshall Triangle we just discussed, is banished exclusively to a separate secondary diagnostic surface.
It's moved entirely out of the primary view.
Let me use an analogy that really clicked for the engineers in my art unit. Think of this interface like the cockpit of an advanced aircraft.
Okay, I'm with you.
In a cockpit, your primary visual instrument is the artificial horizon. You stare at it constantly. You want that artificial horizon to just show you the horizon smoothly and calmly so you can keep the plane level.
Right, you need it to be reliable.
Now, if you have an engine running hot or your oil pressure is dropping, that is critical information. But that information belongs on a separate, dedicated diagnostic dial off to the periphery.
You do not want engine warning lights flashing violently in bright red directly across your artificial horizon while you're trying to land the plane in a storm.
That is a very apt analogy. It is fundamentally about cognitive load management and spatial segregation of data.
The Mach experience orb is your artificial horizon. The Marshall Triangle is your engine diagnostic dial.
Exactly. You can glance at the triangle when you want to diagnose a problem, but your primary visual field remains anchored by the calming, achromatic pulse of the orb.
And we should remind the listener here about the strict data boundaries enforced by this system, particularly when we start talking about the parasympathetic nervous system and biometric intimacy.
Very important point.
The patent explicitly states that even if this system reads physiological inputs, say heart rate variability from a smartwatch or galvanic skin response, the raw biometric telemetry is processed strictly on the dedicated hardware companion.
It is entirely on-device processing.
Yes. Your raw heartbeat never hits a cloud server. Only the derived, anonymized state changes, meaning the resulting mathematical shift in the emotional valence axis of the node state, ever write to the contract.
The actual biometric intimacy is guarded at the silicon level. The system learns your pension without ever transmitting your biology.
Which is a brilliant privacy safeguard.
Uh-huh.
Okay, let's take a breath and unpack where we are in this deep dive.
We've covered a lot.
We have mathematically proven the node state is a rigorous, highly efficient data contract. We have explored the novel, non-obvious triadic visualization of the Marshall Triangle and its midpoint source inversion.
And we have outlined a stress-free UI governed by the separation principle and the man experience orb. The entire foundation is rock solid.
But a foundation is just a foundation. A beautiful interface that perfectly tracks your preferences is still just a passive dashboard. How does this triadic balance actually govern the AI's behavior?
Because the whole premise was that this system achieves shared autonomy.
Right. How does it make the AI sovereign yet obedient?
This is where we transition from a passive UI into an active algorithmic control layer. The Cathedral of Code memos introduce a primitive called the Shared Autonomy Observer.
The observer.
This is the actual governor that regulates the agency between the human and the machine. It takes the tension vector, the mathematical displacement we discussed earlier between the system's current state and the user's calibrated white point, and uses that exact distance to dynamically govern the AI's execution privileges in real time.
It acts as an algorithmic clutch, seamlessly shifting the AI between three distinct operational modes based on the level of tension.
Right. Those three modes are delegate, intervene, and observe. Let's break down how this shifting feels for the user. Think about when you are driving a car.
I love a good automotive analogy.
If you are driving on a straight, clear highway with perfect weather, you turn on cruise control. You trust the car to maintain speed. In COP003, if the mathematical tension is low, meaning the system is highly aligned with the user's calibrated white point, the semantic confidence is high, and the privacy thresholds are met, the observer sits in delegate mode.
This is the cruise control.
The AI is granted the privilege to proceed autonomously. It can execute tasks, draft emails, interact with third-party plugins, all without needing constant, annoying permission prompts.
But what happens when the weather turns bad? What if it starts snowing, or in the system's case, what if the mathematical tension spikes?
If the tension spikes, crossing a preconfigured mathematical threshold, the observer immediately shifts into intervene mode. The AI drops its autonomy.
It hits the brakes.
It halts its execution loop and explicitly asks the user for confirmation or guidance before proceeding. The car gives you the wheel back because it knows the conditions are too complex for cruise control.
And then there's the third mode, observe, which is a fascinating middle ground. In observe mode, the AI proceeds with a task, but it logs every single action silently for subsequent user review.
It's often triggered in scenarios that are low risk but highly personalized, where the AI wants to learn your preferences without interrupting your workflow.
But let's dig into the intervene mode, because what happens when the tension spike is caused by a simple misunderstanding? What happens when the system's semantic confidence drops because you used a colloquialism it didn't recognize?
I absolutely love how the patent handles this. It doesn't just blindly guess, risking a catastrophic error, and it doesn't just crash and throw a standard error 404 command not recognized message.
What does it do?
It issues a semantic restatement.
Explain how a semantic restatement differs from a standard error prompt.
A semantic restatement is an active conversational self-healing mechanism. When semantic confidence drops, the AI generates a natural language interpretation of what it thinks the user meant and presents it for confirmation.
It essentially says, I'm only 60% confident I understood your intent. Did you mean X?
And here's the crucial systems engineering part. When the user corrects it, when they say, no, I meant Y, that correction doesn't just vanish into the ether of a chat log.
It writes directly back to a local semantic calibration profile.
The system fundamentally learns the user's specific semantic idiosyncrasies over time. This permanently lowers the tension for future, similar interactions. The system heals its own misunderstandings.
It is a beautifully elegant interaction loop. But what is truly fascinating here, and I have to give you credit, I had to dig deep into the CTO report provided in our stack of sources to catch this because it differs slightly from the academic preprint, is the underlying mathematics of how this governance is calculated.
Yes, this was a massive red flag for me until I read the actual runtime code-based documentation.
The academic paper on the Marshall Triangle discussed using standard Euclidean distance for measuring the tension from the white point. But the system running in production uses a completely different formula.
It uses a strict harmonic mean to calculate what they call the harmony index. The mathematical formula is h equals 3 over the sum of 1 over e plus 1 over w plus 1 over v, where e, w, and v represent the normalized values of the three axes.
I am so glad you caught that detail because for a patent examiner, the distinction between using a standard arithmetic mean and a strict harmonic mean is the difference between passing a secure system and approving a critically compromised one.
Explain to the listener why that specific mathematical choice is so critical to the patent's claims of security and shared autonomy. Why does the formula matter?
Let me use a mixing board analogy. If the engineers had used a standard average and arithmetic mean, They would simply add the three scores together and divide by 3.
Right.
Let's imagine a scenario where a user system is operating flawlessly on two axes, a 99% performance score and a 99% personalization score.
Sounds great so far.
But there is a severe back-end issue, and they have a catastrophic 10% privacy score. Their data might be leaking.
If you use an arithmetic mean, you average 99, 99, and 10. The result is roughly a 69% overall score.
Exactly. To the system, 69% looks fine overall. The interface would look relatively calm. The May experience orb would pulse gently, and the observer might say perfectly happy in delegate mode, completely ignoring the fact that the user's privacy is deeply compromised.
Which is incredibly dangerous.
It is unacceptable. It is like a mixing board in a recording studio. If you drop the volume of the lead vocals to absolutely 0, it ruins the entire track.
It does not matter how incredibly loud, crisp, and perfect the drums and the bass are playing, the song is broken.
A standard average masks that brokenness by letting the loud instruments drown out the silence. The harmonic mean, however, mathematically prevents this.
Because a harmonic mean disproportionately penalizes the lowest performing axis.
Precisely. In that exact same scenario, 99, 99, and 10, the 10% privacy score drags the entire harmony index down drastically.
It plummets the overall score, instantly tripping the algorithmic threshold, forcefully shifting the observer from delegate to intervene mode, and alerting the user via the Marshall triangle.
The harmonic mean ensures that a critical privacy or security compromise is never masked by high-performance scores in other areas. It is a mathematical failsafe built directly into the core governance engine.
It is brilliant. It takes a mathematical quirk of the harmonic mean and turns it into a foundational security feature. So let's trace the full logic path. The system tracks the node state.
It visualizes the tension.
The observer calculates the harmonic mean. Based on that calculation, the observer has decided whether the AI is allowed to act.
But if the AI is allowed to act, if it's in delegate mode, where does that computation actually happen?
And this brings us to the final major piece of the architecture, adaptive compute routing, or as we call it in the examining unit, the green zone of permitted disclosures.
I am going to push you extremely hard here on the hardware claims, because this is exactly where a lot of ambitious software patents fall apart.
Bring it on.
If this system is dynamically routing massive computational workloads between different execution environments, does the patent attempt to claim the hardware itself? We both know that you cannot just slap a novel software orchestration layer onto a generic smartphone and claim you have invented a completely new physical device.
The USPTO will reject that immediately under the doctrine of abstract ideas tied to generic hardware.
Exactly.
You are entirely correct to push back, and the inventors were clearly well advised because they are incredibly precise here. They adhere strictly to the boundaries of what is patentable.
So what are they claiming?
I want to assure you listening that the physical and industrial design aspects of this system are explicitly outside the scope of this utility patent. The system is designed to act on a general, dedicated hardware companion. It could run on a progressive web app or standard mobile application. They are claiming the method of dynamic routing, the orchestration harness itself, not the physical silicon it eventually runs on.
Good. That keeps the claims clean and prevents a messy 101 rejection based on generic hardware. So explain to me how this dynamic compute routing actually functions in relation to the triadic state we have spent the last 45 minutes discussing. How does the harmonic mean dictate the hardware?
The triadic state, the user's highly specific node state tension vector, drives the physical routing of the compute at the hardware and network level. The system orchestrator maintains at least two cooperating execution environments.
Let's call them Layer 1 and Layer 2.
Correct. Layer 1 is local, on-device compute. Layer 2 is networked cloud compute. If the user's node state biases heavily toward privacy, or if the harmonic mean detects a tension spike that threatens privacy, like we just discussed, the orchestration harness immediately and aggressively routes the computational task to the local, on-device Layer 1 execution environment.
What kind of models are we running locally?
We are talking about running something like a heavily quantized LITER-TLM model directly on the device's neural processing unit, or NPU.
For the listener, quantization essentially means mathematically compressing a massive AI brain so it fits onto a local edge chip without instantly draining the battery or melting the processor.
It is lightweight, it is continuous, and most importantly, the raw data input never leaves the dedicated hardware companion.
It operates entirely in an offline or air-gapped capacity if necessary. The privacy is guaranteed by physics, not just the terms of service agreement.
Yes, but What if the user needs complex reasoning? What if they ask the AI to analyze a massive architectural code base or orchestrate a multi-agent task?
If their node state bias is heavily toward performance over absolute privacy, the local quantized chip simply might not have the parameter count or the memory bandwidth to handle it.
In that case, the routing module dynamically escalates the task to layer 2, a networked cloud environment, but they are very specific in the architectural memos. They aren't just routing this to a generic public cloud.
The sources specify routing to end-to-end encrypted, trusted execution environments, or TEEs.
Exactly. The memos explicitly mention Venice's TEE architecture as an example of this. A trusted execution environment ensures that even though the data is leaving the device, the hardware in the cloud processing it is cryptographically locked.
The cloud provider cannot see the data.
This escalation only ever happens when the performance target absolutely requires it and when the privacy threshold governed by the harmonic mean explicitly permits it.
Do you realize what they have accomplished here? What is truly remarkable about this routing architecture is the complete decoupling of the interface from the back-end models.
Break that down. Why is that decoupling so important for the future of the platform?
In traditional AI apps, the interface is hard-coded to the model. You open a specific app to talk to a specific cloud model. If the company changes the model, or if you lose internet connection, the app breaks. The interface becomes useless.
But in CIP003, the AI model is fundamentally fluid. The routing is governed entirely by the user's calibrated white point and the resulting tension.
Meaning the interface never changes.
Exactly. The interface, the calming Ma experience breathing orb, the diagnostic Marshall triangle, the underlying node state contract remains absolutely visually and functionally identical, whether the backend orchestrator is shifting your query to a local on-device NPU, escalating it to a centralized encrypted T cloud, or, looking 5 years ahead, routing it to a decentralized peer-to-peer compute mesh.
The user never has to change how they interact with the system just because the underlying silicon or infrastructure evolved.
The interface is completely insulated from the back-end hardware wars. If a new, faster chip comes out tomorrow, the orchestrator just adds it as a routing option. The user still just talks to the same quiet breathing orb.
It is future-proofed by design.
Which is the holy grail of systems engineering. Well, I think it is safe to say our drinks are empty, the rain is letting up outside, and we have thoroughly, exhaustively interrogated this stack of documents.
I will happily concede the point, and I will let you stamp this one approved. CIP003 elegantly survives both Section 101 subject matter eligibility and Section 103 obviousness challenges.
It takes what could have been easily dismissed as a vague psychological alignment concept, and it transforms it into a rigorous columnar data contract.
It visualizes that tension through an inverted midpoint source geometry that brilliantly sidesteps existing prior art, and it uses hard math, the strict harmonic mean, to directly govern secure adaptive compute routing across local and encrypted environments. It is without a doubt a highly robust systems engineering architecture.
It really is. It was a pleasure debating this with you. So for you listening, I want to leave you with a final thought to mull over as we close out this deep dive.
I'm all ears.
For decades, since the invention of the graphical user interface, we have designed machines that force human beings to adapt to their logic. We have spent our entire digital lives staring at blinking cursors, learning arcane query syntax, fighting through the overwhelming noise of information overload, and forcefully adapting our human physiology to the rigid, binary demands of software.
But if systems like Quetra succeed,
If they can genuinely entrain to our physiological rhythms through achromatic pacing, if they can accommodate the physical imperfections of our inputs without breaking, and if they can gate their own autonomy based on our triadic tension and harmonic balance, are we finally entering an era where technology actually serves the human field rather than extracting from it?
does the ultimate interface of the future look less like a dense, stressful dashboard of toggles, feeds, and flashing red lights, and more like a silent, attentive, breathing companion?
It's a profound question, and if this patent is any indication, the math to make it happen is already here.
Until next time.
Thanks for joining us in the deep dive.